Previously, we talked about logic gates, things like AND gates and OR gates, and we found that we could perform various logic functions. But the one thing we can't do with logic gates is to remember things. And so in order to put some memory in our circuits, we need to use a concept that's called a flip-flop. And what the flip-flop does is the flip-flop memorizes its states. It memorizes its state. And so we then can use that to compute a current state of the system and then think about going to the next state. So we'll talk about more about states in the next video, but in this video we're just going to look at the flip-flop itself. So the flip-flop is indicated here is a device that has two stable states. The states, why don't we just call them 0 and 1. So the trick here is that when we put the flip-flop in state 0, it stays in state 0 until we put the flip-flop in a different state. If we put it in state 1, it stays in state 1 until we move it to state 0. So we can store information, just one bit of information each flip-flop. But of course, if we use multiple flip-flops, we can store multiple bits, and therefore we can make some fairly complicated things. So there are many types of flip-flops, okay, and they're generally they're indicated by a letter. And so we're using a D flip-flop. We could also use a JK flip-flop or a set reset flip-flop, an SR flip-flop, whatever. And so in the case of a D flip-flop, which is the only flip-flop we're going to deal with, it has two outputs. It has an output that indicates its state and also the complement of the state. It has a data input that we can use to set the data input. We can use to set the state to 1s or 0. It has a clock that tells us when to look at the data, when to change the state. And then it has a set and a reset input. And those are used to initialize the flip-flop. So these are primarily used for initialization. And so we use the inputs, the set, reset, D input, and the clock input to change the state. And then the flip-flop remembers the state until we ask it to change to a new state. And so let's look at the outputs of the flip-flop first, then we'll look at the inputs. The outputs are pretty simple. There's an internal state in the flip-flop. The internal state can be 0 or it can be 1. If the state is 0, the Q output of the flip-flop is 0. And of course, the Q bar output, which is the inverse of Q, is 1. If the state of the flip-flop is 1, we can indicate that because we know that because the Q output is 1. And of course, the Q bar output is 0, just the inverse of that. So the Q and the Q bar are actually fairly simple explanations of how it's fairly easy to understand the role of Q and Q bar. Now let's look at the set and reset. As I indicated earlier, set and reset is primarily used for initialization. And so we use these to initially set whether we want a particular flip-flop to be in a 1 state or a 0 state. When set is equal to 1, Q is forced to 1. So the state goes to 1. When reset is set to 1, the state goes to 0. It's forced to 0. So the easiest way to look at this is a truth table. So we have the values of set and reset. These are all the possible combinations of set and reset values. And this is the result of those set and reset values. When set and reset are both 0, so in this case, set and reset are both 0, the state of the flip-flop is unchanged. Okay, so the flip-flop basically just stays the way it is. When the reset becomes 1, the state becomes 0. When the set becomes 1, the state becomes 1. And in the unlikely event, or I hope it's an unlikely event, that both the set and the reset are 1, this particular flip-flop is designed to ignore the reset and just perform a set function. Now, it's really important to understand that this particular situation, when we simultaneously activate set and reset, depends on the flip-flop, what actually happens. In some flip-flops, the behavior is undefined. So we generally would like to avoid this situation when we do the designs. So that's the role of the set and the reset function. And so we can see this in the set and the reset function. So we have two lines. This is two wires. This wire is normally 0 because we look at this. There's a resistor that's connecting it to 0 potential. So this is ground. Now, in the event that we press this switch, then what happens is this wire is connected. It becomes a 5 volts, okay, which of course is a 1. So if we want to set these 4 flip-flops, we just simply momentarily press that switch. And then that means that Q would be, this Q would be 1, this Q would be 1, this Q would be 1, this Q would be 1. When we release this switch, then these the outputs, the states of these flip-flops will remain at 1. So the flip-floppers remember it. Okay. Conversely, we can go down to this line. By the way, this resistor is poorly drawn, but you knew that. This is normally a 0 here for the same reason we discussed in the upper line. And then so when we push this switch, is that the 0 goes to 5 volts, which of course becomes a logical 1. And then we reset all 4 flip-flops, and then that means all 4 flip-flops would stay at a 0. Okay, so what we would do is we would use this mechanism to initially set or reset the flip-flop. So if we want to set all flip-flops to 1, we press switch 1. If we want to set all the flip-flops to a 0 state, we press the switch S2. Now, this idea of using a resistor to do this is a fairly widely used concept. And so that means that resistor guarantees that the sets are going to be 0 unless we have the button press. Many people will try to design without this resistor. Okay, so just assuming that if there's no signal on this, there's nothing on this wire, that somehow it's magically 0. That could, in many cases, further from the truth. So always take care of your sets and resets. Make sure that they're either 0 potential or, when appropriate, a 1 potential. Now let's go to the last 2 inputs, and that's the clock and the D input. And the D input is the data input. Okay. In this case, what happens is that the D input is ignored until the clock, in this case, because this little up arrow here, until the clock is rising. So when the clock rises, what happens, so this is the clock. When the clock rises in this area, is that we then look at the D input and transfer it to the state of the flip-flop. So when D is 1 and the clock transitions from low to high, as indicated here, that's a rising edge, then Q goes to 1 and it remains at 1, okay, until the state is changed by either set reset or the clock rising again. When D is 0, and the clock does that transition from low to high, then Q goes to 0. And so the truth table is a way of looking at it. In this case, we use this symbol when we talk about the clock rising. So when D is 0, the clock is rising. Q is 0. And this, of course, assuming that the set and resets are all both zeros. And that in order for the clock and data to work correctly, we need to make sure that set and reset are both 0. Conversely, when D is 1, when the clock rises, then we will set Q equal to 1, and then we ignore D when the clock is at 0. We ignore D when the clock is at 1. On the falling edge of the clock, we also ignore D. So the only time we are sensitive to D is during the rising edge of the clock. Now, some flip-flops behave on the falling edge of the clock. So you need to figure out for your flip-flop, you have to understand for your flip-flop, which edge of the clock the flip-flop is sensitive to. Okay, so let's look at some simple examples. The first example is I have a flip-flop. This is a D flip-flop, and it's set and its reset are set to both 0. So the D input and the clock input are the only way to change this state. We are sensitive to the rising edge. So let's assume that the D started, or the state of the flip-flop started at 0. Now notice what happens to the clock. The clock is high. That means it ignores the D input. It won't change the state. The clock is falling. That means it still doesn't change the state. The clock is low. Doesn't change the state. Now the clock is rising. This is when the flip-flop becomes sensitive to the state. So what happens? Becomes sensitive to the input. The input is set to 1 so that we get this transition in the state from 0 to 1. Now what happens is, as we continue, of course this makes no difference, this makes no difference, and the clock going low makes no difference. This makes difference. So the flip-flop transfers the value of D to Q, and that remains at 1. So this flip-flop basically goes from 0 to 1 and remains as 1. Okay, well that's not particularly interesting, but it's called a latch. It just latches the fact that this was a 1. Now let's go through and take a look at the other flip-flop, which is a little bit different because D is no longer constant. D is determined, the value of D is the inverse of the value of the state because it's Q bar. It's fed around here. So let's take a look at it. Okay, here's Q. We assume Q is 0. And then that means Q bar would be 1. And then the clock is running along here. The clock makes no difference until we get to this rising edge. At the rising edge, we transfer D, which is 1 here, into the state. So we transition the state from a 0 to a 1. Now the state is 1. Okay, now with the state going 1, when Q goes to 1, then doesn't Q bar go to 0? So we get a 0 now for Q bar. And now D is equal to Q bar. The flip-flop ignores D during this region until we get the rising edge again. And then this 0 that's in D will be transferred to Q. And so what happens here is that we are changing the state of the flip-flop on every rising edge of the clock, which is kind of neat because the following is that we look at Q. Q is a waveform, a periodic waveform, and it has the following features. It has twice the period of the clock. So here's the clock's period. Here's the period of Q. So it has half the frequency. And also it's symmetric, which means that this distance up here is the same as this distance when it's low. The time duration is low. So this is a square wave, where this actually was maybe an output of 555, where this top piece was twice as wide as the bottom piece. So we can use this for squaring up a clock, which we actually did when we worked with the 555 clock. Okay, let's look at a really simple example here, and this is a ripple binary counter. What we're going to do is we're going to use the previous example, and we're just going to string a bunch of those previous examples together. So it looks worse than it is. So let's take a look at it. There's 4 flip-flops here, and let's say this is Q1, this is Q2, this is Q3, and this is Q4. And so we wire these all the same way. But this is not Q, this is Q bar. So we're taking Q bar, the inverse of the state, and we're feeding it back to D, just as we did in the previous example. By the way, we do this for all of these. We're feeding back to D, and we're feeding back to D, and we're feeding back to D. Okay. Now what we do is we also take the Q1 bar and we run it to the clock of the next flip-flop as indicated here. And of course we set the set and reset both to 0. And so let's take a look at our clock. Our input clock is going to change the value of Q1 bar, okay, every rising edge. So here's our clock. Our clock is rising edges here. And so what happens? We change the state of Q1. Here's the rising edge here. We change the state here. The rising edge here. We change the state here, etc. Okay, now what happens is what's happening to Q2? Well, isn't Q1 Q2's clock? So the same thing happens. On the rising edge here of Q1, we're changing the state of Q2. The rising edge of Q1, we're changing the state of Q2. And then also, since Q2 is Q3's clock, we have the rising edge of Q3, and it's changing the state of Q3. So what this is this is just a binary counter. Okay, it's counting from 1, 1, 1, 1, 2, 1, 1, 1, 0, 2, 1, 1, 0, 1, 2, 0, 0, 0, 0, and then it repeats. And so if you look at this thing running, it repeats in that manner. So this is actually a very, very quick way of building this counter. The only issue with this counter is that the counter is rippling. And rippling means the following. It means that when this value changes state, so this value changes state here, this value on the next one will change state, a few nanoseconds later. This value changes states a few nanoseconds later. This value changes states a few nanoseconds later. So what happens is we ripple this state as the state is going through, and we have a delay between when this value changes and when that value changes. This can cause problems if we're using these outputs for looking for specific values. So we generally don't use a ripple counter, but it's a nice way to just look at a simple example. Okay, let's do a shift register on this. And the shift register looks something like this. It's a little bit more complicated. We have our 4 flip-flops, and let's look at the set and reset lines. This flip-flop we never reset it. This flip-flop we never set it. This flip-flop we don't set. This flip-flop we don't set, so we can wire it this way. The reset line, or the initialization line, is running to this reset, this reset, this reset, and it comes up and runs to this set. So what we have with the initialization is when we push this initialization button is that we set this flip-flop and reset the other 3. So we get a 1, 0, 0, 1 when we initialize it. So now what happens when the clock comes through? As the clock is pulsing in this line, okay, and it's also, notice it's pulsing here, pulsing here, pulsing here. We transfer the value of the first stage to the second stage. So we transfer here. So this 1 goes to this flip-flop. So now this flip-flop becomes a 1. Now this flip-flop was a 0, so that 0 is propagated to the third flip-flop. And then this was 0, so this is propagated to the fourth flip-flop. And then finally, this was a 0 because of initialization, and this 0 is propagated around to the first flip-flop. So what we do is we go from 1, 0, 0, 0 to 0, 1, 0, 0. So we moved the 1 over. We shifted it over by 1 place. If we now look at it again, is that this now had the 1 in it. So now the 1 goes over to the third position. The 0 from the third position goes to the fourth position. The fourth position moves the 0 over to the first position. So we have 0, 0, 1, 0 and 0, 0, 0, 1. What happens after 0, 0, 0, 1? It runs back from the fourth flip-flop around to the first flip-flop, and it repeats. So this is just shifting this 1 to the right for each rising edge of the clock. So this is what this shift or the ring or the shift register looks like. Okay, this shows that counting pattern I alluded to earlier. That it's shifting over, and then when it's finished at Q4, it runs back here, and then it goes along like this, and it shifts. So it's zigzagging through here. This is what the timing diagram looks like. It's sometimes harder to see with the timing diagram, but let's look at it. The first thing we know with the timing diagram is this dotted square or box indicates that we don't know whether Q1 was in a 1 position or a 0 position. Similar for Q2, Q3, Q4. We are going to press the initialization switch. So now the set and reset lines become active. So now we will be setting the first flip-flop to 1, and then the second, third, and fourth to 0. Now, we wait until the clock rises. So when the clock rises, we now do our transfer. So now the first flip-flop content is moved to the second one. The second flip-flop content is moved to the third one. The third one is moved to the fourth one, etc. Okay, oh, and I forgot this, that the fourth ones, okay, is moved over here to the first one. That's this loop that comes up around here. So then that continues, that process continues. Can you see the 1 moving? The 1 started here, now the 1's here, now the 1's here, now the 1's here, and then after this transfer of the clock moves the 1 from the fourth flip-flop up to the first flip-flop as indicated here. So we're just looking at it in different ways. We can look at it as a circuit, we can look at it as a table, we can look at it as a timing diagram. Okay, this is the pinout of the flip-flop we're using. So when you build these things, you need to kind of look at this pinout. It's not particularly involved. The first thing to notice is you always have to put 5 volts here and you have to put ground here. Okay, failure to do that means it won't work. There are 2 flip-flops, and so we would put a bundling board down the middle, and so flip-flop 1 happens to have its outputs along pin 1, pin 2. Okay, here's your clock. Okay, here's the reset, and here's the set, and here's the D or the data input. So you just put them along there. This pattern is repeated identically on the other side. In order to figure out which way is pin 14 and pin 1 versus pin 8 and pin 7, this has a little notch here in the edge of it. So that's important that you don't put this thing in backwards. Okay, flip it around. So this is the pinout, and just watch this pinout as you actually use it. This is my design of a very simple counter. This is, I think, the ripple counter. And so let's take a look at it. Is that we have the power supply over here. We had that. That's our power supply. Here's the 555 timer sitting in here. And then we hook the 555, pin 3 of the 555 timer. We bring it over here and drop it into the clock. on this flip-flop. And then this is that dual flip-flop through here. Notice that the edge of this is right up here. That's that little notch I talked about. And so this is the flip-flop, and we would be wiring a flip-flop identically to the way that we wired the binary counter. And so we would just basically use this half flip-flop, the lower half, and we wired it as a clock to the top half. I didn't wire this one. This would be the other. This would be the second one, and this would be the third flip-flop over here. I used a little LED, so I put a resistor here, current limiting resistor, to light an LED so I could see the output of the second flip-flop. And so it's pretty straightforward to do it. You just have to kind of make sure that you keep everything clean and understand that it needs to be correctly wired. This is the ground for the second flip-flop, and here is the power for the second flip-flop along here. Okay, so we have that. So let's see what kind of assignments we can give you. Okay, we'd like you to build, design, and verify a 3-bit that has 3 flip-flop binary counter. The counter should count in the following sequence. So we give you the sequence there. And then use 3 LEDs to indicate the state, the Q1, Q2, and Q3 state to verify the counting. We ask you to use transistors to drive the LEDs because the LEDs it's possible they'll pull too much current out of the flip-flops and cause the flip-flops to not operate. So you can use transistors, or if you wanted to, you could use an inverter here. I can go either way on that. So what we do is we put an inverter, and then we would put our LED, and then we put a resistor to ground. And so we would, again, this inverter would buffer the LED a little bit for us. But I think the easiest way is just put the transistors. So that's your assignment, and make sure that you document that assignment, and so that somebody with similar knowledge to you would understand what you did, could repeat your experiment, and get the same result. That's the end of this discussion.